This is the Unit 3 video number 3, and we are on page 3 looking at the electron configuration. An atom's electron configuration is its arrangement of electrons. The electron configuration represents all of the electrons as well as their locations in the atom. So, to determine an atom's ground state, which is the simplest electron configuration, we have 3 rules that we look at. Now remember, before I get into this, let me explain the term ground state again. Remember with the Bohr model of the atom, there were these orbits, and the lower energy levels were closer to the nucleus, and the further you get away, the higher energy it is. I think of this type of thing like a ladder. So here's a basic ladder, and here's the ground. So as far as the amount of energy that an orbital has, or an electron, it could correspond with the rungs of a ladder. So a lower rung would have some amount of energy, but a rung that's way up here would have a lot more energy. If you fell from the first ladder rung, it probably wouldn't hurt that bad. You might even land on your feet. If you fall from the top of a ladder, then you might have a lot more issues because there's a lot more energy associated with being up high on a ladder. As far as the ground state is concerned, my question for you is, in this ladder analogy, where is the least amount of energy? Where could you fall and have the least amount of energy, have the greatest chance of being okay? And the answer to that is the ground. The least possible energy when you're standing in front of a ladder is to be on the ground and not be on the ladder at all. So this is the lowest possible energy level for a ladder, and basically the same idea here. The atom's ground state is the lowest possible energy configuration. In this unit, we're only working with neutrally charged atoms. This means the number of protons and the number of electrons are equal. So when we want to know how many electrons does an atom have, we can look at the atomic number. This is the whole number in each box on the periodic table. So for instance, hydrogen is 1, helium is 2, lithium is 3, beryllium is 4, boron is 5, carbon 6, nitrogen 7, oxygen 8, fluorine 9, neon 10, and so on. The whole number. In our classroom periodic table, this number is blue. On the printout that I gave you, all the numbers are black, but this one is always going to be a whole number. So when we talk about making an atom's ground state, there's really 3 ideas, and I'm going to go through them just for familiarity's sake, and it'll make it a little bit easier when we represent the electron configurations. There are 3 rules. The first one is called the Aufbau principle. Aufbau is a German word. It means built upon. So this rule says that electrons occupy the lowest energy orbital before filling any higher energy orbitals. If we're talking about a ladder, that means we're going to stand on the ground, and then our next step would be the first ladder rung. We're going to take the steps in order, take the energy levels in order. I also think of it somewhat like filling a glass of water. So here's a glass, and I'm going to pour in some water. The water has to occupy the bottom of the glass first before it can fill the top levels of the glass. And it fills up something like this. There is no situation on our planet, at least, where we can have a glass of water and we start pouring in the water and it fills up here and then goes down, assuming that the glass was actually empty. The second idea is the Pauli exclusion principle. And this says that electrons spin as they travel around the nucleus, just like the planets. So think about Earth and maybe the drawings or the videos that you've seen about Earth. And Earth is going around the sun in an orbit, but Earth is also spinning on its axis. So the spin on its axis is giving us days, and the going around the sun in the orbit gives us years. The same kind of idea with electrons. Electrons spin as they travel around the nucleus. It's possible they could spin clockwise or they could spin counterclockwise. Either one is a possibility. The Pauli exclusion principle states that an orbital can hold a maximum of 2 electrons. And this is important. They have to have opposite spins. So, kind of like the idea with magnets, if you put the north pole of 2 magnets together, it doesn't want to stick. It's that idea of opposites attracting. So when we represent these later, an orbital is going to be represented by a box, just a box like this. Here's the orbital. And as far as the electrons and their spins, here's an electron with a spin in one direction. Here's an electron with a spin in a different direction. And so when an orbital is holding 2 electrons with opposite spins, then we would have a picture that looks like this. And this all plays into the Pauli exclusion principle. The next one, Hund's rule. Electrons have a negative charge. We've already talked about that. But they have a tendency to repel each other. Remember, the same idea, opposites attract, but the same, they tend to repel. So anything with a negative charge, like all electrons, they don't want to get too close. They want to push each other apart, and they want to be as far apart as they can be. Hund's rule says that single electrons must occupy different orbitals in a given sublevel before a second electron can occupy the same one. When I think of Hund's rule, I really think of a school bus. So if you get on the bus, let's say you're one of the first people on for your route, there's going to be a lot of empty seats. And you're going to choose an empty seat, maybe across the aisle from a friend. The bus has a lot of room, so you and your friend are not going to get into the same seat this early. Most people are going to choose an empty seat when it's available. So what you find is that about halfway through the bus route, every seat on the bus has one student in it with room for a second. The second person is going to sit in your seat only after all of the seats have at least one person. Same idea with Hund's rule. The electrons will each occupy different orbitals in a sublevel, and they won't double up until they have to.